Welcome to the deep dive. Looks like we're going deep on software engineering today, huh? Specifically, the Google way of doing things.
Yeah, it seems like you've given us a pretty hefty stack of stuff to get through.
Oh yeah, we've got the Software Engineering at Google book itself, plus some articles on code search and handling those massive changes they do.
It sounds like you're interested in more than just how to write code. You want to see how software lives, grows, and even eventually how it sort of fades away.
Exactly. This feels like a whole ecosystem, not just lines of code in a file.
It is. It's about understanding how Google builds and maintains these huge software systems, especially with the unique challenges they face.
Right, right. It's not just about being a good programmer, it's about the whole software engineering mindset.
Exactly. We're talking about Google's engineering culture, their practices, the tools they use, all of that.
Okay, so one thing that jumps out from the book right away is this distinction between programming and software engineering. Is that just a fancy title or what?
Well, they make a big deal about it for a reason. Think about it like this. Building a house versus building a skyscraper. Both involve construction, right?
Yeah.
But the scale, the planning, the long-term thinking you need are completely different. Software engineering is realizing that your code's going to be around for a while, needs to be maintained. It might be worked on by huge teams.
Okay, so it's acknowledging that code has a lifespan. It's not just a one-and-done thing.
And that it's constantly evolving. The requirements change, the team grows, and you have to adapt. It's not just about getting it working right now.
Gotcha, gotcha. And they even compare it to entropy, which I thought was pretty wild.
It's a great analogy. They talk about this thing called Hiram's Law.
Hiram's Law.
Yeah, it basically says that when enough people use a piece of code, even its accidental behaviors, its quirks, become part of its identity. You can't just change those things easily without breaking things. Like imagine you build a tool and there's a bug in it, but someone figures out this weird workaround, and then everyone starts using that workaround as if it's a feature.
Oh, I've seen that happen.
Right. And now you can't fix the original bug because you'll break everyone's workflow. That's Hiram's Law in action.
So even if my code seems to work, there might be these hidden dependencies lurking that I don't even realize.
Exactly. It's like a time bomb waiting to go off. And the larger your system, the more users you have, the bigger the potential for these hidden dependencies to cause problems.
That's kind of terrifying. Okay, so thinking long-term from the start is crucial.
Absolutely. You have to anticipate how your code will be used, how it might evolve, and plan accordingly.
The book spends a lot of time on teamwork at Google, too. What's their secret sauce? What makes their team so effective?
They talk about this googly attitude, which sounds kind of cheesy, but it boils down to some core values.
Like what?
Humility, respect for each other, trust. They believe in collaboration, not cutthroat competition. Open communication, where people can freely share ideas and concerns.
They gave that example about a team arguing for months about where to put a widget on a web page.
Oh yeah, classic. It makes you realize that sometimes the best technical solution isn't enough if you don't have a team that can actually work together effectively.
So it's more about the people than just the technical skills, in a way.
It's about creating an environment where everyone feels safe to speak up, to admit when they don't know something, to ask for help. They call it psychological safety.
So no one's afraid to look dumb or rock the boat.
Exactly. And that leads to better knowledge sharing, faster problem solving, and ultimately a stronger product.
Okay, that makes sense. Now, onto something I think most engineers dread. Documentation.
Ah, yes. The love-hate relationship with documentation.
The book makes the argument that it's as important as the code itself, but I mean,
Yeah.
come on, who really likes writing docs?
I hear ya, but they have a point. Think about it like this. You write some code today, it works great. 6 months later, you come back to it. Do you remember exactly how it works? Why you made certain choices?
Probably not, unless it's really well commented.
Right. And that's where good documentation shines. It's not just about what the code does. It's about the why. It's about capturing the knowledge and context that would otherwise be lost, making the code much easier to maintain in the long run.
Okay, but they had problems with documentation. I feel like I've heard about internal Google wikis becoming a graveyard of outdated info.
Oh, yeah. They've definitely learned some hard lessons along the way. They talk about how their wiki became this unreliable source because no one was keeping things updated.
So it's not enough to just write it, you have to maintain it too.
Exactly. The key takeaway is to treat documentation like code. Version control it, review it, keep it up to date. It's an ongoing process.
So it becomes part of the development lifecycle, not just an afterthought.
Exactly. It's a living document that evolves with the code base.
Okay, so documentation. Less of a chore, more of a living history of the code base. Interesting. Now let's talk about testing. The book goes deep on unit testing, of course, but it also emphasizes larger scale testing strategies.
Right, because as systems get more complex, you can't just rely on testing individual components in isolation. You need to test how those components interact with each other in a more realistic environment.
So it's like you can test all the parts of a car engine individually, but you still need to make sure the whole engine works when it's assembled, right?
Exactly. Google has this layered approach. Small, fast unit tests for individual functions and modules, and then larger integration tests that simulate real-world scenarios.
I bet those larger tests can get pretty slow and resource intensive.
They can, for sure. But the book talks about techniques they use to mitigate that, like hermetic testing.
Hermetic testing, what's that?
Think of it as creating a perfectly controlled environment for your tests, where you can eliminate any external factors that might influence the results.
So you're isolating the thing you're testing, making sure the results are consistent and repeatable?
Right, it's like creating a mini laboratory for each test. And they also heavily automate their testing to make running these tests more efficient.
So it's about striking a balance, finding ways to test thoroughly without slowing down development too much.
Exactly. And this leads us to another key concept: continuous integration and continuous delivery.
Ah, yes, CI/CD. It feels like everyone's talking about this these days.
And for good reason. It's a fundamental part of Google's engineering culture. It's all about automating the process of building, testing, and deploying code.
So instead of these big, infrequent releases, they're constantly pushing out small changes.
Yep. It's about catching errors early and often, reducing the risk of introducing bugs into production.
But doesn't that require a ton of infrastructure and tooling to support? I mean, constantly building and testing, that's got to be resource intensive.
It is, and Google has invested heavily in systems to support this. They have this global continuous build system called TAP, which is pretty incredible.
Wow, so they have the resources to really commit to this approach.
They do, but the underlying principles are something any team can learn from.
Mm-hmm.
Make small, incremental changes, test them thoroughly, and integrate them frequently. It reduces the risk and makes the whole process more manageable.
That makes sense. Okay, so we've got testing, we've got continuous integration. What else? Oh, one thing that really resonated with me from the book was their discussion of dependency management.
Ah, yes. The joys of dealing with external code.
That can be such a headache. You never know what might break when you update a library.
Tell me about it. Google's had their fair share of struggles with this. They talk about cases where they ended up using 2 different versions of the same library internally, which caused all sorts of problems.
Yikes.
Right. Now they're really big on enforcing a one-version rule, making sure everyone uses the same version of a dependency.
So it's about controlling those external factors as much as possible.
Exactly. And they also try to be good citizens in the open source world by prioritizing stability in their own projects, so they're not causing the same headaches for others.
That's great. Okay, we've covered a lot of ground here, but there's one more thing I have to ask about. Large-scale changes.
The infamous LSCs.
Yes. How do they handle refactoring millions of lines of code? It boggles my mind.
It's definitely not for the faint of heart. They have a whole system for managing these massive changes with specialized tools and processes.
Like what? How do you even begin to approach something that big?
One key tool is called Rosie. It's basically an automated refactoring tool that can analyze the entire code base and make changes across thousands of files.
Wow, so it's like having an army of robots doing the tedious work for you.
Kind of. It allows engineers to make sweeping changes in a safe and controlled way without introducing a bunch of errors.
That's incredible. So it's like a superpower for managing complexity.
Exactly. It empowers engineers to tackle problems that would otherwise be nearly impossible to handle manually. But there's a lot more to it than just the tools. There's a whole human side to managing these changes.
Right, because you've got thousands of engineers working on the same code base. How do you coordinate all that?
That's something we'll dive into in the next part of our deep dive. We'll talk about code review at Google, how they handle communication and collaboration, and some of their strategies for minimizing disruption during these massive changes.
Sounds good. I'm definitely eager to learn more about that. So stay tuned for part 2, where we'll uncover the secrets of large-scale change management at Google.
Welcome back to our deep dive on Google's approach to software engineering.
I'm still thinking about all that stuff from last time, especially those huge code changes they do. Like, wow.
Those LSCs are definitely impressive.
Yeah, it's wild to think about refactoring millions of lines of code.
It's a testament to their engineering skills, that's for sure.
Absolutely.
But before we jump back into LSCs, you mentioned code review at the end of the last part.
Oh, right. We do code reviews at my company too, but I have a feeling it's a whole different beast at Google.
You're probably right. At Google, code review is deeply ingrained in their culture. It's not just about catching bugs, it's about knowledge sharing, ensuring quality, and maintaining consistency across that massive code base.
So it's like a built-in mentorship program almost, where everyone's learning from each other.
Exactly. They have this dedicated tool called Critique to streamline the process. It lets more experienced engineers share their expertise with newer team members, and it helps everyone stay on the same page with coding standards and best practices.
They mentioned using static analysis tools as part of this code review process. What are those and how do they help?
Imagine you have a second pair of eyes constantly checking your code, even before a human sees it. That's what static analysis tools do. They scan the code for potential issues, like bugs, security vulnerabilities, and style violations, without actually running it.
So it's like a safety net that catches those little mistakes before they become big problems.
Precisely. And it gives human reviewers more time to focus on the bigger picture, like design and readability.
Speaking of readability, the book stresses writing code that's easy for humans to understand. Why is that so important at Google?
Well, think about it this way. If code is difficult to read, it's a nightmare to maintain.
Right. Oh, for sure. It's like trying to decipher a secret code.
Right. And when you have a code base as huge as Google's, readability is absolutely crucial. They have this whole readability process where engineers get extra code reviews when they're new to a language, just focusing on style and best practices.
So it's about making sure everyone's writing code in a similar way, which makes it easier for anyone to understand and work with any part of the code base.
Exactly. They want to avoid the code base becoming this jumbled mess of different styles, which would be impossible to manage.
It's like you wouldn't want to read a book where every chapter was written in a different font, right?
Exactly. Consistency is key.
Okay, let's go back to those LSCs, those massive code changes. We talked about tools like Rosie for refactoring, but how do they even decide when such a big change is needed?
It's usually a combination of factors like changing business needs, platform upgrades, or just addressing technical debt that's built up over time. Sometimes it's about improving performance or security. Other times it's about just making the code easier to maintain.
So it's about making sure the code base stays healthy and can adapt to new challenges.
Exactly. And just like with a big home renovation, you need a solid plan before you start tearing down walls. The first step is identifying why they need an LSC and defining exactly what needs to change.
So they have to figure out what they want to achieve and what parts of the code will be affected.
Exactly. That in itself can be a huge task, involving input from multiple teams and careful analysis of potential impacts. Once they've got a clearer scope, they develop a detailed plan, outlining the steps and the tools they'll use.
We talked about Rosie, but are there other tools specifically for managing these LSCs?
Oh yeah, definitely. They have a tool called Cider. It's really helpful for migrating code to new APIs. Let's say Google wants to swap out an old API for a new one. Cider can scan the entire code base, find everywhere the old API is used, and even suggest or automatically make changes to use the new API.
Wow, so instead of manually updating millions of lines of code, Cider can basically do it for them.
Pretty much. It streamlines the whole process and makes sure changes are consistent, minimizing errors.
It makes me wonder how they keep things running smoothly during all these constant changes. It's like trying to change a car's engine while it's still driving down the freeway.
That's a great analogy. And that brings us back to that idea of continuous delivery, which is a big part of Google's engineering philosophy.
Yeah.
It's all about automating the release process so code can be deployed quickly and safely, even with all these ongoing changes.
We touched on this before, but it seems really tightly connected to all these other things we've been talking about, like small changes, constant testing, all that.
Absolutely. Continuous delivery, or CD, goes hand in hand with their commitment to continuous improvement. It's about having a smooth and reliable pipeline to get code from a developer's computer to actual users.
The book mentioned that Google releases new versions of some products multiple times per day. How do they do that without things constantly breaking? I'd be terrified.
It takes a lot of work and careful planning, that's for sure. They have super sophisticated monitoring and alerting systems to catch problems fast. If something goes wrong, they can automatically roll back the changes like an instant undo button.
So it's like a self-healing system that can recover from issues automatically.
Exactly. But even with those safeguards, they still need to make sure new features don't mess up the user experience. That's where things like feature flags and A/B testing come in.
Oh, right, feature flags. That's where you
Yeah.
can turn new features on or off without actually redeploying the whole code base, right?
Yep, exactly. It's like having a control panel for the software, letting them test new things out and roll them back quickly if there are problems.
And A/B testing is where you compare different versions of something to see which one performs better.
You got it. Google uses this all the time to make data-driven decisions. They might test different versions of a button or a web page layout to see which one gets more clicks or conversions.
So it's like a scientific experiment, but for software. They can see what users actually respond to instead of just guessing.
Exactly. It helps them continuously improve their products. But with all these constant releases, tests, and data analysis, they need a ton of computing power. It's like they need a whole other engine just to power their development machine.
Right. The book mentioned this thing called compute as a service. What's that all about?
That's a perfect way to describe it. Compute as a service is Google's internal infrastructure that gives their teams computing power on demand. It's a huge distributed system that supports all their products and services.
So instead of having dedicated servers for each project, they have this pool of computing power that can be shared and scaled up as needed.
Exactly. And managing that infrastructure is a huge challenge. That's where Borg comes in. It's their cluster management system, basically the brains behind orchestrating all these machines.
So Borg is like the conductor of an orchestra, making sure all the instruments are playing in sync.
That's a good way to put it. Borg handles things like resource allocation, task scheduling, even failures, all automatically. It keeps everything running smoothly.
The book also mentioned containers. How do those fit into the picture?
Imagine you're packing for a trip, and instead of just throwing everything randomly into your suitcase, you use those packing cubes to keep things organized and separate. Containers are kind of like packing cubes for software. They're a lightweight way to package and run applications.
So instead of installing software directly onto a server, you bundle it into a container that can run anywhere.
You got it. Google has been using containers internally for years, and they've played a key role in scaling their services.
This reminds me of Kubernetes, that open source container orchestration system. Doesn't that come from Google?
You're absolutely right. Kubernetes is based on Borg and uses many of the same ideas. Google took their knowledge and shared it with the world, making container orchestration much more accessible.
That's amazing. It's cool to see how their internal innovations have influenced the whole industry.
It shows their dedication to pushing the boundaries of tech and sharing what they learn. But let's get back to those large-scale changes, the LSCs. We've talked about Rosie and Cider, but I'm wondering about the people involved. How do they coordinate thousands of engineers working on the same code base?
Yeah, that's got to be a challenge.
Communication and collaboration are crucial, especially when dealing with changes across multiple teams. They have a system for proposing, reviewing, and approving LSCs, making sure everyone is in the loop and the impact is carefully considered.
So it's a structured process to prevent chaos.
Definitely. And to minimize disruptions and keep the code base stable during these massive changes, they rely heavily on trunk-based development. It means everyone works directly on the main branch of the code, what he called the trunk.
Wait, no separate feature branches. That sounds kind of risky.
It might seem that way, but they've found that working directly on the trunk leads to faster integration and fewer merge conflicts in the long run.
But how do they keep the trunk from becoming a complete mess if everyone's constantly making changes?
That's where their heavy reliance on automated testing and continuous integration comes in. Every change is thoroughly checked before it gets added to the trunk, like a safety net.
So it's a high-trust environment where everyone's responsible for writing good code and testing it well.
Exactly. It's all about shared ownership and accountability.
With all that code and all those engineers, finding the right piece of code must feel like finding a needle in a haystack. How do they handle that?
They have this powerful tool simply called code search. It lets engineers search through the whole code base quickly and efficiently.
So it's like Google search, but specifically for code.
Pretty much. It understands code, so you can search for specific keywords, functions, file paths, even code patterns. It's a vital tool for navigating their massive code base.
This whole deep dive has been so eye-opening. We've talked about their monorepo, their build system, continuous delivery, their infrastructure, and even those strategies for managing those crazy huge changes. It's clear they've built a seriously impressive development ecosystem.
It's a testament to their engineering excellence, that's for sure. And even though their scale is unique, the principles and practices they use can be valuable lessons for any software team, big or small.
Absolutely. It's been an amazing journey, and I want to thank you for guiding us through this world of software engineering at Google.
It's been my pleasure. I hope our listeners have enjoyed the deep dive and learned some new things.
Me too. And to our listeners, if you want to learn even more, definitely check out the book, Software Engineering at Google, and explore the other resources we've mentioned. Until next time, keep on coding.
Welcome back to the deep dive, ready to wrap up our exploration of Google's software engineering world.
Definitely. We've covered so much already, from those mind-boggling large-scale changes to their continuous delivery pipeline. It's been quite a journey. It really has. It's like we got a peek behind the curtain at how one of the biggest tech companies in the world builds software. And at the end of last time, we were starting to talk about compute as a service, that massive engine that powers everything at Google.
It is a massive engine. At Google, compute as a service refers to their internal infrastructure that provides on-demand computing resources. It's like a giant distributed network of machines that can be dynamically allocated to run all their different products and services.
So instead of having dedicated servers for each project, they have this flexible pool of computing power they can share and scale as needed. That's pretty smart.
Very smart, and definitely not easy to manage. That's where Borg comes in. Is Google's cluster management system, the brains behind the operation, making sure all these machines work together seamlessly.
Borg's like the conductor of an orchestra, making sure all the instruments are playing in harmony.
Exactly. Borg handles resource allocation, task scheduling, and can even handle failures gracefully, making sure that all their systems are running smoothly and efficiently.
We keep coming back to the theme of scale and how Google has to solve problems differently because of it. Then the book also mentions containers. How do those fit into this whole picture? I know containers are becoming super popular in the software industry, but I'm still a little fuzzy on what they actually do.
Think of it this way. You're packing for a trip. Instead of tossing everything randomly into your suitcase, you use packing cubes to organize your clothes and keep things separate. Right. Containers are like those packing cubes, but for software. They offer a lightweight and portable way to package and run applications.
So instead of installing a bunch of software directly onto a server, you bundle it all neatly into a container that can run anywhere that supports containers.
Exactly. And Google has been using containers internally for a long time. They've been essential for scaling their services because containers create a layer of isolation that makes it easier to manage dependencies and deploy software reliably.
That makes sense. It's all about controlling the environment so things work consistently no matter where they're running. And this reminds me of Kubernetes, the open source container orchestration system. Didn't that come from Google?
It did. Kubernetes is actually based on Borg and shares a lot of the same principles and design. Google took their expertise and released it to the world, making container orchestration more accessible for everyone.
It's pretty awesome. It's cool to see how Google's internal tools and innovations end up impacting the entire software industry. Okay, let's go back to those large-scale changes, the LSCs. We've talked about tools like Rosie and Cider that help with the technical side, but I'm curious about the human element. How do they coordinate all those engineers working on the same code base during these massive changes?
That's a really good question, and communication is key. Google has a structured system for proposing, reviewing, and approving LSCs to ensure that everyone's on the same page. They carefully assess the potential impact of these changes before they even start.
It sounds like a pretty rigorous process. Do they have specific strategies for minimizing disruption and making sure the code base stays stable while these changes are happening?
One of their core principles is trunk-based development. This means all engineers work directly on the main branch of the code base, often called the trunk.
Wait, hold on. No feature branches. That sounds kind of risky. I always thought branches were important for isolating changes and avoiding conflicts.
It is a different way of working than a lot of companies are used to. But Google has found that working directly on the trunk actually encourages faster integration and reduces the chances of merge conflicts later on.
Okay, I can see how that might work, but how do they prevent the trunk from becoming unstable if everyone's always committing changes to it? That sounds like it could easily turn into a disaster.
They rely heavily on those automated tests we talked about before, and continuous integration is also key. Every change is thoroughly vetted before it gets merged into the trunk. It acts like a safety net to catch potential problems before they impact the entire code base.
So it's a high-trust environment. Everyone's expected to write high-quality code and test their changes carefully. It's like a collective responsibility to keep things working.
Exactly. And all of that leads to a smoother, more efficient development process.
I can see how that would work at Google scale.
Yeah.
But with so much code and so many engineers, finding the right piece of code must be incredibly difficult. It's got to be like searching for a needle in a haystack.
Huh.
How do Google engineers deal with that?
Well, they have this incredibly powerful tool called code search. It allows them to search their entire code base quickly and efficiently.
So it's like Google search, but for code.
Exactly. It understands the structure and meaning of code, so engineers can search for specific keywords, function names, file paths, even code patterns. It's an invaluable tool that helps them navigate the complexities of their massive code base.
Wow. We've been on quite a journey with this deep dive. We've explored their monorepo, their build system, continuous delivery, their compute infrastructure, and even how they manage those massive code changes. It's been fascinating to see how Google has created such a sophisticated and effective software development ecosystem.
It's a testament to their commitment to engineering excellence and their constant drive to innovate. And while their scale might be unique, the principles and practices they use offer valuable lessons for software teams of all sizes.
I completely agree. It's been an amazing learning experience, and I want to thank you for guiding us through this fascinating world of software engineering at Google.
The pleasure was all mine. I hope you and our listeners have enjoyed the deep dive and learned something new along the way.
We definitely have. And to our listeners, if you're interested in going even deeper, we highly recommend checking out software engineering at Google and exploring the other resources we've mentioned throughout this deep dive. Until next time, keep exploring, keep learning, and keep building amazing software.